Okay, can I start? Okay, let me start. So welcome everyone. I'm happy to see so many people here interested in a topic that has absolutely nothing to do with what we are doing here. This is about security in quantum world. Before I worked with Cliqz, I did a PhD in quantum information theory, or more precisely on quantum cryptography, and this talk is kind of the remnants of that. Actually, this talk is more of an overview over all sorts of things. So I haven't been working on most of these things, actually, maybe a little bit on the last part. So all of this, explaining this and giving this talk is also totally new to me. So bear that in mind, and yeah, you can ask questions, but just notice that maybe the talk is not always that polished and that smooth, and that's because I have never, ever in my life given an overview like this. So it's the first time for me as well. All right, I will jump right into the matter. Actually, I will show you something that you all are very familiar with. We are all very familiar with classical physics. We'll here, when we talk about classical, it's what is opposed to quantum. Classical objects, for example, like this thing here, they have certain properties that we are very, very familiar with. For example, we know where this thing is, right? We can always see its position. And can you catch? And if you guys follow this one here now, while I'm throwing it, you will also notice that all of you have seen the whole time where it is, and at the same time also how fast it's going and in which direction it is going. And this is particular about classical objects. When we go to quantum mechanics, to quantum physics, so basically at atomic scales where we're talking about molecules and atoms or photons, so things on the order of 10 to the minus 10 meters, it's also called an Armstrong, then things become different. Then we have quantum objects. And there we have this phenomenon that, of course, we can know its position very well. We have a quantum particle, we know exactly where it is. But at the same time, we cannot know where it is going. So we don't know anything about its velocity or the direction, or more precisely, the momentum. Similarly, we might do the opposite. We might want to know exactly its direction. For example, here, this apple's direction denoted by this kind of movement. But at the same time, we cannot know the position. And this is called Heisenberg's uncertainty principle. So we can know position and momentum accurately if we want, but we cannot know them accurately at the same time. I would like to give you a brief history of quantum mechanics before going on with about cryptography, about classical cryptography, how it is now, about quantum computing and why it is a threat to cryptography, and finally about quantum key distribution or quantum cryptography. So quantum mechanics emerged around 1900. Before that, people thought that things are already known and everything's in physics is known, and so basically we don't need to do anything anymore. And actually, Planck was the first person to really dive into or dig out these quantum mechanical things around 1900. And actually he was apparently, that's the legend, advised not to study physics because apparently physics was already all known before that. But he still studied physics, and then he explained a phenomenon, which is the black body radiation, which basically led to the idea that light is emitted in quanta rather than as a continuum. We have already seen black body radiation in another Brownbag talk. I don't know if you guys remember, but it was in Salvador's talk. It was if you remember, there was this cosmic microwave background. Hello? Marty. No? Okay. Oh, look, this works. All right. No? Really? Okay. Seems like it's working again. Okay, I'll try to keep going until I get shut down again. Yeah, anyway, so in Salvador's talk, you remember maybe the cosmic microwave background, which was this 2 or 3 degree Kelvin background that you could hear, that people observed in the 60s. That is the remnant of the Big Bang, and that's actually the thing that Planck discovered in 1900. It's the same thing, just he discovered it in a different scenario, basically. Yeah, so, and that was the start of quantum mechanics. Lots of things have happened since then. 1905, Einstein explained another phenomenon where he really, when Planck was very shy to say that actually photons or light is a discrete particle. Planck was very careful about this, and he didn't want to make these statements. What he basically said is like it's a mathematical trick to make it work, but he didn't really stand behind his own theory. Only later Einstein, he picked it up and said, yes, in fact, what if we take this idea one step further and we really say that light is actually a quantum particle. So he was the one who introduced the photons, starting from Planck's idea. Later on, between the 1910 and 1930, a lot of new ideas sparked, a lot of new things came, a lot of people worked on these things, and they came up with all sorts of other interesting things, all sorts of other things that came out of the theory of quantum mechanics. There was also a good, strong mathematical formulation of the problem. 1927, Heisenberg came up with the uncertainty principle, the thing that I've shown you before. Let's see again.
I literally changed the batteries on that, like, just then.
Okay. Ah, now it's working again. I don't know. I feel like...
This one died as well?
No, it's working. I just have to keep switching between the two. Yeah, that's what I'm saying, like it's the uncertainty principle or something like that. All right, so this is like is it working? Yeah, good. So there is a bit of a gap in this slide between 1927 and 1981. That's a long time where it doesn't mean that nothing happened. A lot of things happened there, but I'm not going to talk about them, and I'm not going to mention them here, because basically 1981 was again when things started to go in a different direction, namely in the direction of quantum computing and quantum cryptography, because at that time suddenly people realized that quantum mechanics is not just cool for nature, but it can also be useful for us to basically do faster computations. And that's what Feynman noticed in 1981. He suggested that one could do a quantum computer, a system that computes totally differently than a normal computer, a classical computer. And he wanted basically to simulate quantum systems with this quantum computer. Shortly after that, in 1984, that's actually a very important date for quantum cryptography, because that's when quantum cryptography came up. Bennett and Brassard proposed their first cryptographic system that could basically transmit information, or one could exchange information in a much more secure way. Their protocol was actually called BB84 after their first name, well, the first initials and the year. And 1994, another very important date, is when Shor proposed his factoring algorithm. as maybe some of you will already know, and I will show later in the talk, factoring is the fundamental principle behind current cryptographic systems, or actually the fact that factoring a large number into its prime components is very difficult. This is why current cryptography systems work, or how they work. And in '94, Shor showed that there are quantum algorithms that can factor much faster than what we currently know, and this would be a problem. So there are two more points that I would like to mention here. 2004, Idée Quantique kind of made a commercial quantum cryptographic system which they brought on the market, so one can buy this and one can really do quantum cryptography at home. The thing is really expensive, I assume, and it's basically being bought by banks or governments or universities for demonstration purposes. And and for quantum computing, 2016, there was a first 12-qubit quantum computer. I will tell you a little bit later about what qubits are. So this is basically, there are some demonstrations of these things. So there are things that are quantum computers and quantum crypto systems already out there on the market, or at least in some labs and for demonstration purposes. All right, any more questions? Good. So I would like to go into the first topic, a bit of a background on cryptography. This is a very rough overview over what is cryptography, how does it work, and this is all classical cryptography, so how people have been doing and are doing things. The need for secure communication has been around forever. Basically, the Romans already wanted to do that. And what cryptography is actually a way for two legitimate parties to exchange a message without leaking it to anybody else. So in cryptography, there's these two legitimate parties. They are typically called Alex and Bobstery. And there is always this anybody else, this other person, and that's actually the eavesdropper. I'm not saying anything about that. So these are the main players in cryptography, and so the kind of the most normal or the most obvious thing that one would want to do is kind of say that, well, Alice and Bob, they have a shared secret key. So they have a secret between the two of them that only they know. And based on this secret, they are able to kind of encode and decode some message. So for example, here is a message. And using the key, Alice can create a thing called ciphertext, which is just a garbled up version of the message that doesn't mean anything. And she can then send this to Bob, who with the use of his key can decode the message as well. And so if you don't have the access to this key, you cannot do anything with the ciphertext because it's just nonsense to you. So the first type of this kind of encoding that I'd like to present to you is a very nice little example here, is the Cesar cipher. I'm sure everyone heard of this. The key here is basically to garble up the alphabet by basically shifting the letters in the alphabet by some predefined value. So for example, here an A becomes a T, a B becomes a U, a C becomes a V. And so if you have this text here, a private browser with integrated search, you can turn it into this thing here. Could anyone please read this? I don't know. This is like totally cryptic for us. And this is something that has been used by the Romans, this idea. However, I mean, it's very easy to decipher this. It's like very easy to basically rotate through the whole alphabet and then figure out what the message was. Also, you can do some sort of frequency analysis. I'm sure you've all heard of this. You can see that there's a lot of E's in the first message and a lot of X's in the last message, and then you know that E and X is probably the same. So you already know the shift of the things. And as you see, this kind of way of doing things is not very safe. But it's a first start. There are more safe things. For example, the one-time pad. This is a kind of a binary sequence of zeros and ones, let's say. So if you have a message, here this dragon fruit, and you kind of encode it in zeros and ones, and you do an XOR, so you kind of add it to this key, then you will get a cipher text which looks very much the same as the key, so it's just some random zeros and ones, and only if you have this exact same random key can you decipher it. Now, this is a very good thing, actually, because it's provably safe. Because if you don't know this key, then you cannot do anything with this message here in the middle. It could be any message. So like, if you don't know the key, this green field could represent any image. And this type of encryption is very good, it's very safe. But there is a problem, right? Like you all probably already know that. So let's say I want to use it again because it's so safe and so cool. So let me just do this thing again, and then I can just encode everything with this key, and I'm fine. Why don't we do this? Well, that's exactly the problem. This key is only safe if you use it once. And I have a little demonstration for you here. Let's see if this works. Oh, how do I make this smaller? Marty. Where? On the left. Zoom. Ah, here. Okay. Ah, much better. All right, let's see if that works. So the gray square is the key. The green and the red squares are the messages. So if I take this key, this is actually called visual cryptography, if you've never seen this. You can take this key and basically move it on top of here, and you should be able to decode. If you move it really well on top, it's not working very well on this computer. Yeah, but it's not, okay. Anyway, so you see that if this was somehow more flexible to move, you could see you can see this decoding here. Similarly, I can go over here, and I can decode another message, right? So these are the two messages that I have. But the problem is, as I said, you cannot use the key twice. Why? Well, imagine somebody has the green and the red message. Well, what could they do with it? They don't see anything in the green and the red themselves, but they can do the following thing. They can take the red and put it on top of the green. And it's kind of hard to see here because of the screen, but you can basically, by putting the two messages on top of each other, you get the sum of the original messages. So you can discover, you could see, if this was a bit better, that there is a smiley and the text on top of it. And so basically, if you have access to two of these ciphertexts, then this thing is absolutely not secure. So the thing is, that's why it's called one-time pad, so you can only use it once. Okay. And that's why actually this one-time pad is not very often used unless you really want to encrypt something once and you don't mind having to exchange a large sequence of random bits that you can then throw out. There is another way how things are done these days, and that's public key cryptography, for example, RSA. The principle behind this is totally different. So there's each person has two keys, basically a private key and a public key. The public key is kind of used for encryption, and it is very easy to compute. So if you have a plain text or a message and you want to encrypt it, you use your public key, and that's a very easy operation. However, on the other hand, the ciphertext is decrypted with a private key, and if you don't have the private key, then this direction is very, very difficult to go. The security of the system relies on the fact that it's very hard to break the private key, so the blue arrow here is very difficult to go if you don't know the key. So RSA actually relies on something called prime factoring. So the easy part is to multiply two prime numbers, or two numbers, and the hard part is basically to find the components of this. So for example, 5 times 3 is very easily computed to 15, but it's harder to decompose 15 into 3 and 5. Now, maybe you don't believe me, but let's say RSA 180, this is a key with 180 digits. Now, I mean, each of you could technically take these two numbers on the left and multiply them together. But if you were to be asked to find the prime factors of this monster, that's a hard task. Here we are talking about 180 digits. So this actually, this number here is actually already not safe at current standards. These days we are talking more about 2,000, 3,000 digits of key length for safety. Okay, so I've shown you a little bit of cryptography. Mainly I've shown you how things, what is safe, the one-time pad, if you use it once, and RSA, which is kind of a very convenient thing to use, but its safety relies on a mechanism which is factoring of large numbers. And this is where quantum computing comes into the game. So quantum computing, proposed by Feynman, is very different from classical computing. So in classical computers, you have transistors, diodes, you calculate with bits 0 and 1. While in quantum computers, you have some kind of quantum particles, atoms, molecules, and you compute with a totally different degree of freedom, like spin or polarization. So I'd like to show you this a little bit more in detail. So a classical bit, what a classical computer computes with can be either 0 or 1. So the for example, an electron could be in box 0, so in the left one, or in the right box here, and this would be considered bit 0 or bit 1. And this is very standard, like it's very normal for everyone to consider this. However, if you were to look at a quantum bit, it can be in a superposition, and that means that the particle can be at the same time in both boxes. This is another one of these weird quantum phenomena that we, as normal, well, in a classical world, never would experience something like this. This is very good if you want to, for example, so quantum computing uses this fact, because if you can not only compute with either the 0 or the 1, but you can compute with it at the same time, so you can kind of use the two things at the same time, then you have quite a bit of more power. And I'd like to show you in this little demonstration, or in this little video, how that happens. So a classical computer, if you want to solve a problem, we solve it basically sequentially, like we have bits of zeros and ones, and we calculate with them normally. We have like a one-track, like a linear way of doing it. However, in a quantum computer, you can do things simultaneously, and let's see if this kind of video demonstrates that. It's a bit slow to start. So basically, a classical computer would try to find its way out of this maze by going like one ball at a time, trying to find the best way. And so basically you have to go one after the other until in the end you find the exit. If you were to have a quantum computer, you can do this simultaneously. So you have like a ball that is simultaneously everywhere, and it's simultaneously searching for all the paths, and therefore can much faster figure out the end, however, only probabilistically. Any questions about this? Good, because this is really not intuitive. So what is this good for? Like if we can simultaneously compute things, kind of simultaneously compute things, well, this is, for example, useful to solve certain very difficult problems, such as factoring. And that was 1994 when Shor came up with his factoring algorithm on a quantum computer. Now, factoring a large number that I've shown you before is very hard. So for classically, so let's say you have here the number of bits that the number consists of. I've shown you a 180-digit number that was somewhere here. And you'll see that this is the time it takes to factor that number, and here we have 1 second, 100 seconds, and here we are up with 1,000 years and 1,000,000 years. So this white line here is what classical algorithms can do. So how fast they can decompose a large number into its prime factors. So for example, 1,000-bit number would take 1,000 years to decompose with the current best known classical algorithm. However, on a quantum computer, this can be done within seconds. So you can see where the threat comes in terms of RSA, which relies on the fact that it's hard to decompose a prime number into its factors. And that's where quantum computers pose a large threat. Okay, that's actually all I would like to say about quantum computers. And now I'd like to go on and say, well, what can we do against a world in which there is a quantum computer that can break our current algorithms? And that's where quantum key distribution comes in. Now, quantum key distribution is not exactly quantum cryptography, because as you can see, it says key distribution. So what it is about is based on the one-time pad. We want to be able to generate these kind of secret keys that then can be later on used for a one-time pad, which is really safe, but in a very secure way. And that's kind of quantum cryptography. It's invulnerable against all sorts of, against any new algorithms, whether that's on a classical computer or on a quantum computer, because it does not rely on difficult mathematical problems, but it relies on fundamental quantum mechanical laws. So actually, I've already almost shown you everything, every phenomenon in quantum mechanics that is being used in quantum cryptography. So remember Heisenberg's uncertainty principle. Although we can measure position and momentum accurately, we cannot do it at the same time. And remember that there was this encoding of the bit into, for example, of an electron in the left box or the right box. So similarly, we could say that, well, we encode something either in a position direction, so we can say the left box or the right box is a 0 or 1, or we can also do this for a momentum. So for example, an upward or downward movement versus horizontal or vertical versus horizontal movement could also be considered a 0 or 1. The thing is that if you don't know in which encoding you are, right? If you don't know whether your bit is encoded in position or in momentum, you will not be able to determine it with arbitrary accuracy. Does that make sense? Kind of? A little bit? Okay. So, and this principle that we are not able to measure everything accurately, right? This means that there is some kind of secret or some kind of hidden knowledge behind certain things, and that's what is used in quantum cryptography as well. So let me try to explain this in a little example. I'm not sure that I will be able to explain everything that well and to that detail, because yeah, I haven't been able to figure out a very good deductive way how to do this, but let me try anyway. So the way that quantum key distribution happens is basically Alice wants to send a bit 1, for example, to Bob, And she can encode this now, for example, in position. She can say that, all right, I'm sending a position bit, and they establish a quantum channel. This can be either a fiber or even free space, over which Alice sends this bit to Bob. Now, Alice knew in which basis she put it. Here it's the position basis. And Bob doesn't know in which basis Alice sends stuff. He just gets something. So he can keep this thing and maybe later decide, or even at some point decide to measure it. And if he decides to measure it in position basis, then he will get the correct bit out of it, right? If he decides to measure in the momentum basis, he will not be able to get anything out of this because it's just going to be a random bit for him. So depending on what Bob decides, this will give him the right outcome or not. However, well, this is kind of good, but actually what this really is good against is an eavesdropper. So if there's an eavesdropper who tries to also measure this bit, if the eavesdropper also doesn't know whether it was a position or a momentum encoding, then they will also not be able to figure out this information. And moreover, not only that, but by measuring it or by interacting with it, they kind of destroy the system, they disturb it, and they kind of turn it into something else that then is, for example, sent on to Bob. And this allows them, Alice and Bob, to notice whether someone has been messing around with their channel. And they can later on see that something is not okay if their channel is putting or displaying too many errors. And so there is this kind of idea that the more errors you see, the more information leaked out of your quantum system. And so you cannot tolerate arbitrary many errors. And because if you do, then you could potentially assume that someone tampered with your channel. So this is not everything yet. This is actually the full BB84 protocol. It's very similar to what I was just trying to explain, but in real detail. I don't know if you want to hear this still, if you still want to know a bit more about this. Basically, it is done with, typically is done with photons, so not apples and other things. So these photons, they can have different polarization directions, so horizontal, vertical, or diagonal 45 plus minus 45 degrees. And these kind of polarization modes of the photon behave like position and momentum. They cannot be known at the same time. And so we can use these degrees of freedom to send information from a sender, Alice, to a receiver, Bob. And depending on who measures in which bases, Alice and Bob can establish a random number of bits that then they can use later on as a key. There is this part in between where they have to do some kind of post-processing, so just the sending of the information and measuring is not enough. They have to do a bit more of work afterwards, and so that's actually a bit more of an involved thing than just sending things back and forth. Okay. With this, I'd like to already finish my talk. I guess it was a little shorter than expected. If you have any questions, please shoot. This was very, very overview and very high level. I know that. I have actually no idea who knows how much about these things, so I really just wanted to give you a little glance into these kind of things. Yeah, and thanks to everyone who participated.
I do have a question. I still don't get the exchange from the key. How does Bob know if it's diagonally or whatever?
That's
momentum?
Exactly the question that I was expecting, because he doesn't. He doesn't know. And this is what I was skipping over here. And so the way this works, okay, I guess I have to explain this a bit more in detail. So Alice chooses a bit sequence 1 or 0, right? And then she encodes in one or the other basis, so in the red-orange or the bluish one. And Bob does the measurement, and your question is, how does he know which one Alice sent? Well, he doesn't. He randomly picks one or the other. But that means that half of the time he will be right. He will be picked the same basis as Alice. And half of the time he will be wrong, and he picked the wrong basis. And that's what this step here was that I was just swiping under the rug afterwards, that they have to afterwards, when they've measured everything, they do a step called reconciliation, where they pick a small sample of their bits that they measured, and they compare them, and they check how much agreement is there. And they will know that 50% is actually in the wrong basis. So in the first step, they take all their signals, and they do a step called sifting, where they throw away all those bases where they did not match. Okay, so the ones that matched, when Alice has a 0, definitely Bob also has a 0, and when Alice has a 1, definitely Bob also has a 1, if they had the matching bases. But if it didn't match, it doesn't matter, because then it's just random. So they do, actually, to answer your question, this is the sifting step, where they basically throw away half of their signal in order to sift out those that match. And then they have matching bases measured. And then comes the second step, where they, among the matching ones, they take some part and they compare how much errors are there do they see. Because if they see a lot of errors in a random sample that should match, then they know that an eavesdropper was in between and messed up with it. So in the end, actually, only 25% of the signal kind of remains in a way.
Well, so the physics in quantum is that they have an undefined state. Schrödinger Katze, that's your discipline. So is that what happens when you have an eavesdropper? So you know actually the state of the particle at the moment you measure.
Yes, so basically Alice knows what she sent, right? Alice prepares, in this case, a 0 or 1 in position or momentum space. And she knows what she sent, and she knows what Bob should obtain if he measured in the right basis. Now let's say Bob measured in the right basis and he didn't obtain the right thing. Then they will know that something happened in the channel that disturbed the state. So yes, because Alice knows what she sent, she can make sure that things were sent properly to Bob. Does that make sense? Does that answer your question? Yeah, sure, we can do that. Mirror?
If we are losing 75% of the data that we are communicating, is it like really cost effective or no?
So first of all, these are photons. They are very easily generated, and you can generate them at a very high rate and a lot. The problem is more that the traveling of the photons through the space. So whether this is free space by basically taking a laser and shining it to the next building or to the receiver somewhere, or whether sending it through some optical fiber, there is a lot of loss within the optical fiber itself. And just as much as errors contribute to a potential eavesdropper, so does loss. So when you lose photons, it could also be attributed to an eavesdropper, because the eavesdropper could just take the photon and keep it, and who knows what else happens in such a channel. So in typical scenarios with lasers, for example, loss is a big problem. And so these protocols are not so much limited by the sifting and the reconciliation step of Alice and Bob, but more because of loss and because it's hard to create single photons. Another thing about your question, so this is a very like an example of how to do it, right? There are other ideas where you do not send 50% position and 50% momentum space, but you could do a biased version where you send 90% momentum or 90% position for the key generation and 10% of the other bases for checking. So it's a bit like testing and checking proportions between the two, and so you can make a lot more key bits, right? You can create a lot more key bits by sacrificing on the testing bits. So that is possible if you don't want to lose so many. However, as I said, it's not the sifting that is a big problem, but the transmission loss in the channel itself.
So first, you didn't explain like why quantum computers are like more effective, because like it was actually a question about that device, that qubits. How many quantum, I don't know, like spaces that it had? Did it actually work? And so yeah, you talked about the device that was actually bought by banking industry and so on. And how many like cells did it have?
So that device that I mentioned, this is actually a quantum cryptographic system, so a thing like this, and not a quantum computer. The quantum computers, so these quantum crypto systems, they exist, they run, they work, maybe not at a very large distance, because as I said to Humera, this is the problem, the transmission. About quantum computers, well, that's actually, it's not very much my topic. Quantum computers are very, I mean, I don't know if, probably some people understand how they work. I don't know in detail how things work. There is a million different suggestions how to do it and experiments, and they run with, I mean, I showed you in 2012 there was a 12 qubit computer, so 12 particles were being addressed. So it's not a big thing, and it's all in experimental mode right now still. If you are referring to the D-wave computer, I don't know if that's what you meant.
Oh, I actually was asking like how many qubits did it have?
D-wave.
No, the 12.
The 12 qubit computer.
Did it work?
Well, I assume that it works. So they probably, I didn't check their experiment exactly, but that's kind of the maximum that has been reported, and 12 is not very high. So when you say did it work, probably it did, so probably it did something, but as you can see 12 qubits is not big, so it's still in its initial state, I would say.
Yes, thank you. Yeah.
Excuse me. Those thing with 12 qubits computers, they were able to sum up digits. So that's most. I mean, whatever D-wave means, it mostly does not work, and it doesn't give up any speed up. And the D-wave architecture does not permit actually doing Shor algorithms, as far as I understand.
So as far as I know, D-wave, I mean, D-wave is using something like adiabatic computing.
Yeah,
and they can solve basically one problem. However they do it, it's not really clear, so it's very intransparent, right? They are not, they do not say how many qubits they have, for example, because maybe it's also hard to judge what, but anyway, so it's a bit of a unclear thing there with D-wave. However, a 12 qubit computer, the one that I mentioned here, this is not D-wave, this is done in a lab. So I assume that that's probably really 12 qubit quantum computer that they, well, I mean, whatever that is, it's like an experiment.
May I ask then a question about this 12 bits? So, I mean, in qubits in general, perhaps that's again not the area of talk, but for example, those problems that they want to solve fast, like, I don't know, minimization, for example. So this basically means that you solve the, you take a Hamiltonian, you put the I and then d psi dt, and you try to, instead of adiabatic evolution, you look at the I wouldn't call it quantum. I mean, you look at the Schrödinger evolution, right? And you hope that you will have a tunneling from the one minimal state to the other. But how it can actually, in general, work?
I see your point. So you seem to know about adiabatic computing, or actually, that's how it sounds to me, because the quantum computer, the way that these things work, you really try to, again, I haven't been working on this, and this is like far away from me, but you are working on, you take individual, so for example, you take artificial atoms, or sometimes even real atoms, and you try to isolate them in some sort of, let's say, lattice or in a grid or something, and you really have kind of a qubit system in each atom, right? Like each atom, you take, I don't know, electron spin up and down of one of the orbiting electrons, or if you are able to make a quantum dot, you can artificially generate this binary qubit system in really an atom. And you do not do adiabatic quantum computing in a regular quantum computer, but you actually address each of these atoms with some sort of pulses and lasers or whatever other tools, kind of, to and start to manipulate the atom itself. So you really make a kind of a quantum gate that actually, so you don't look at the whole Hamiltonian of the system, but you can actually do like, or you do on the whole thing, but you kind of do transformations on the whole system in the space of that atomic system. So it's not adiabatic, but it's controlled.
And what's next? I mean, you did the it's similar to like the back what you described. So you have the super cooled thing, these qubits, then you do some change, and you, in general, you have to start your computation from zero.
Yes.
Wait till you reach the same, right? Is it?
Yeah,
Well,
you kind of initialize in, I don't know, 0, 0, 0 or
Should be.
something, and then you do your gate, which transforms your system into a superposition and entangled large state over everything, and then you do a measurement in the end, and you get a measurement outcome. Again, probabilistically in the right system. But you, as I said, like if you have 4 qubits or even 12 qubits, this is very small, and it can be easily beaten by a classical computer. You don't need a quantum computer for this size, right?
Should be very expensive also to.
Huh?
Should be very expensive also to run.
Well, yes. I mean, there is a lot of people working on this and trying to make these things, and you need like all sorts of equipment and people to do it. And yeah, it's still an experimental and research phase, so that's definitely expensive for the whole infrastructure and maintenance and testing and all that. But yeah, does that kind of answer your question
Yeah,
about
because I was always wondering. I mean,
there's
yeah,
a total
it's
difference between adiabatic
yeah.
computing and this
Yeah.
very controlled computing where
yeah,
you
I understand.
take those little guys and jointly transform them directedly.
Thank you.
More questions? Thank you.